Section 1.2, Variables, Expressions, and Equations. We're going to start with some terminology here at the beginning of the section. On page 36 at the bottom, the first bold-faced term we see is constant. And it says, a constant is a fixed, unchanging number. So something like 2 or 7 or pi. The next sentence defines a variable. A variable is a symbol, usually a letter, used to represent an unknown number. Now, you've been dealing with these since elementary school. Do you remember the worksheets where you had to fill in the empty box? 1 plus empty box is 3. And you'd fill in your empty box with a 2. Some of us had worksheets that used question marks. And now in algebra, for our variables, we will typically use letters. And here x would be 2. A variable is a symbol, usually a letter, used to represent some unknown number. Once you get to trig, that can be expanded to Greek letters. You'll have your theta, your alpha. We'll probably just stick with regular letters for this course. The next term they define is an algebraic expression. Here at the bottom of page 36, an algebraic expression. It says an algebraic expression is a sequence of constants, variables, operation symbols, and/or grouping symbols formed according to the rules of algebra. So something like 2 times the quantity, x plus 3 minus 4. There's an algebraic expression. It contains constants, variables, operative symbols, grouping symbols, and it is formed according to the rules of algebra. Let me ask you this. 5y, is this an algebraic expression? Notice when we define algebraic expression, it says and or. It says an algebraic expression is a sequence of constants, variables, operative symbols, and or grouping symbols. So it doesn't have to contain them all. So is 5y without any grouping symbols? Is that an algebraic expression? Yes, because it contains at least some of those. What about just a variable by itself? Just z. Is that an algebraic expression? Yes. What about just a number? 6. Is that an algebraic expression? Yes, because it contains at least one of those items, constants, variables, operative symbols, and or grouping symbols. So these are all algebraic expressions. On page 38, we have a few more terms to get out of the way before we start looking at problems. Here on page 38, just below the center of the page, under Objective 3, we define an equation. An equation, it says, is a statement that two algebraic expressions are equal. Well, here's an algebraic expression, 1 plus x. Here's an algebraic expression, 3. And here's a statement that the two are equal. So there's an equation, very straightforward. And of course, an equation will always contain an equal sign. It is absolutely vital that you be able to distinguish between expressions and equations. We continue in this same paragraph to notice it does say an equation always includes the equality symbol, and then next it defines to solve an equation. What does it mean to solve an equation? It says to solve an equation means to find a value of the variable that makes the equation true. So back in our little equation from first grade, what value of the variable makes that statement true? When x is 2. Because when I plug 2 back in for x, I get a true statement. It goes on to say, defining the term solution, that such a value of the variable, this 2, such a value of the variable is a solution of the equation. So we've got our terminology out of the way. Let's move over to the homework set. You can join me on page 40. Let's take a look first at number 5. I know I usually save the odds for you, but I want to take a look at this here in lecture. Number 5 says, explain why 2x cubed is not the same as 2x times 2x times 2x. Why are these not the same? Well, I thought when you cube something, you multiply it times itself 3 times. But what did we say last time? It is important to be able to identify the base of the power. And with the order of operations in mind, which holds rank? Which is more powerful? An exponent or a multiplication right here? The exponent pulls rank. So what is that exponent attached to? Just the x. If I were to expand this expression, the 2 is just sitting out front, multiplying this x cubed. The only thing being cubed is the x. So this would be the equivalent expanded form. If I wanted to write an exponential form for 2x times 2x times 2x, I would want to cube the 2x. And how am I going to show that? With parentheses. This lets the 2x be the base of that 3. And so what are we cubing? In this first expression, just the x, the 2 sitting out front. In my expression here, what am I cubing? What is the base? That whole 2x, the whole thing, is being cubed. Number 6. Number 6 says, why are 7 less than a number and 7 is less than a number, translated differently? Now this refers back to the types of problems that they were doing in example 3 on page 38, right there under objective 2, translating. Why are these translated differently? Let's look at the last one first. 7 is less than a number. A number, we're just going to call that x because it's an unknown. 7 is less than a number. 7 is less than a number. Now, how does that differ from this first phrase? 7 less than a number. 7 less than a number, without the is, that doesn't mean is less than. Here, less than indicates subtraction. 7 less than a number. 7 subtracted from a number. 7 less than a number. X minus 7. Notice that 7 minus x would be wrong. Because that would be a number less 7. A number subtracted from 7. You can't turn a subtraction around and expect to get the same answer. So be very careful with the order as you deal with subtractions and divisions as well. One thing that she's going to have you doing in this section is evaluating expressions given values of the variable. Let's turn our attention to number 18. Number 18 in the homework set, the instructions: find the value of each expression. Now, what have I said I'm going to write on a quiz or a test? That is the same as saying evaluate. And looking at number 18, we want to evaluate the expression 4x minus 1 over 3x given, let's do part A, given that x is 4. All that means to do is plug 4 in for x and what? Crank out the answer. So let's plug 4 in for x. We have 4 times x is 4 minus 1 all over 3 times x is 4. So plug 4 in for x, and now you know what to do. Following the order of operations, we'll work top and bottom separately until we can finally divide using that fraction bar. In the top, 4 times 4 is 16. We'll finish that in a minute. In the bottom, 3 times 4 is 12. Back to the top, 16 minus 1 is 15, and the bottom is already done. We've simplified the top and bottom of the fraction, so we're now ready to divide. And class, what is 15 divided by 12? It does not divide out evenly, so what are we responsible for doing? Reducing to lowest terms. There's a factor of 3 contained top and bottom, so dividing the top and bottom by 3, this reduces to 5/4. So what is 15 divided by 12? 5/4. And as we said last time, it is preferred to leave these as improper fractions, that is, reduced to lowest terms. In algebra, we prefer improper fractions typically to mixed numbers. Certainly I would count it right if you wrote 1 1/4, but there's no need to. And in most applications, we would need to change it back to 5/4 anyway. Let's do another one of these. Let's take number 20. And this time, let's do part B. Number 20 says evaluate 2x plus x squared, given, part B, that x is 6. So we plug 6 in for x. 2 times x is 6 plus x is 6 squared. Evaluate, crank it out. Order of operations says the first thing that we'll do here is deal with that power. Now honestly, because the multiplication is the very next thing, and these are independent of each other, that is, one is not waiting on the answer from the other to keep going, we could do the multiplication in this same first step. I'm going to take it a piece at a time right now. 6 squared, 6 times 6 is 36. Next we'll tackle that multiplication. 2 times 6 is 12. And finally, the addition is the only thing left to do. We have a total of 48. Let's have a look now at number 30, a similar problem. We're plugging in for variables and evaluating. This time we have 2 different variables, and we've got some fractions. Those are always fun. Let's do part A on this one. Here in number 30, we want to evaluate x fifths plus y fourths, given that x is 2 and y is 1. Plug in, crank it out. We plug in 2 for x, plug in 1 for y, and to add fractions, of course, we need a common denominator. Least common denominator here is 20. We'll need a factor of 4 on our first fraction. We'll need to multiply top and bottom by 5 on the second. This gives me 8 twentieths plus 5 twentieths. 8 of them plus 5 of them totals 13 of them. 13 twentieths. Make sure your fraction's in lowest terms. It is. Put a box around it and be done. Let's grab number 34 while we're here. And this time we'll do part B. On a quiz, it would look like this. Evaluate 6x squared plus 4y given, and part B says that x is 1 and y is 5. Actually, I'd like you to try this one without me. So go ahead and pause the video, crank that out, and when you get your answer, come on back and we will compare. All right, we need to plug in for our variables first. 6 times x is 1, and it's being squared, plus 4 times y is 5. And now just follow the order of operations. Let's get this power out of the way first. 1 squared. 1 times 1 is 1. We're ready to do the multiplications. I can do them both in this same step. 6 times 1 is 6. 4 times 5 is 20. And finally we add to get a total of 26. How'd you do? The next thing we want to take a look at is this idea of translating from English to algebra. We're actually gearing up in these problems to deal with word problems later in chapter 2. But we're going to go ahead and start practicing the little pieces at this point. Look at number 40. In number 40, it reads 15 times a number. The instructions, it says write write each word phrase as an algebraic expression. She says using x for the variable. I'm not worried about what we use for the variable, but we'll go ahead and follow her instructions. 15 times a number, very simple. 15x, 15 times some number. Number 42, 6 added to a number. I want to think about this one very carefully. 6 added to a number. What does it sound like was there already? And what am I doing to it? It sounds like I already had some number, and to that I added 6. So I will write 6 added to a number. Now question, do I have to count it right if you write 6 plus x? Yes, because addition can be turned around. You would still get the same answer. So I would have to count that right. But I prefer to get into this habit of writing it this first way. 6 added to a number. Because, consider now number 44. 7 subtracted from a number. Seven is being subtracted from the number you already had. So I will write 7 subtracted from. 7 subtracted from a number. Realize that this is different, as we mentioned earlier, than writing 7 minus x. You cannot turn a subtraction around and expect to get the same answer. For this reason, because you cannot turn subtraction around, I prefer to stay in the habit even when we're talking about addition. And when it says 6 added 2, I'm going to write something plus 6. Do I have to count this one right? Yes. But be careful, because subtraction cannot be turned around. Number 46. Number 46 says a number subtracted from a number subtracted from 4. So what does it sound like is happening here? What's being subtracted and in which direction? A number subtracted from 4. It sounds like I already had the 4 from the outset. And from that 4, I'm subtracting some number x. A number subtracted from, right? A number subtracted from 4. Can't turn that one around. Subtraction, you cannot turn subtraction around and get the same answer. So if you put x minus 4, I'd have to count it wrong. A number subtracted from 4. Now compare this to number 48. It says the difference. The difference of 8 and a number. The difference means what? The difference is the answer to a subtraction problem. So we're subtracting. The difference of 8 and a number. When it uses the language like this, the difference of, you take the expressions in the order they appear. The difference of a number, the difference of 8 and a number is going to be 8 minus that number. When it says the difference of, you take it in the order that it appears. In fact, let's take a moment here and go over a few terms. What do I call the answer to an addition problem? The answer to an addition problem is called the sum. In the problem we just worked, the answer to a subtraction problem is called the difference. Do you remember what we call the answer to a multiplication problem? When we multiply two things, the result is called the product. And the answer to a division problem? The answer to a division problem, the quotient. So these are terms you need to be familiar with as they're used in these phrases, as they're used in word problems here in the future. And you will hear me use these words just as I describe the steps in going through a problem. So be sure that you are familiar with them. Now typically we see the sum of this and that, the product of this and that, the quotient of this and that. In number 48, it said the difference of. Another common way to talk about a difference, though, is to say the difference between. And honestly, on a quiz or a test, that's probably the language you will see me use. Your book will say the difference of. I will very likely say the difference between. So just be aware of that. Let's do a couple more of these translating problems. Number 50. a number divided by 18. A number divided by 18. Well, that's very simple. A number divided by 18. However, nothing wrong with this, but in an algebra class, I want you to become very accustomed to the idea that when we talk about a division, we are typically going to use a fraction bar. So the preferred form of this answer, nothing wrong with this, but the preferred form of this answer would be a number divided by 18. In fact, when you look the answer up in the back of a book in the back of this book for a problem like that, you will find it written as a fraction. I'd have to count this one right, but here in an algebra class, let's go ahead and get used to writing these divisions using our fraction bar. Number 52. Number 52. The product of 9 and 5 more than a number. The product of 9 and 5 more than a number. Take this a piece at a time. Think about what it's saying. It says the product of, so we know we're what? We're multiplying. What are we multiplying? The product of this and that. The product of 9 and the rest of it. So this and is your multiplication sign. The product of this and that. So, the product. So far I've written the product in algebra, that dot right there. The product of what? This and that. The product of what? 9 on one side and on the other. 5 more than a number. 5 more than a number. 5 more than a number. And I've got to count that wrong. I've got to count that one wrong. This is the product of 9 and a number plus 5. Order of operations would have me doing the multiplication first. If I want this to be a multiplication problem of 9 times the rest of it, what do I need? This would have to be in parentheses. Now I'm multiplying 9 times the rest of it. The rest of it being 5 more than a number. Now that we see how that looks, I see I don't need the dot. The cleanest form of the answer would look like this. Nothing wrong with this. If you've already put the dot, why bother writing another step? But if we think a little bit ahead and see that we're going to need those parentheses anyway, we could write this cleaner form of the answer. Either way works. But I have to have those parentheses, otherwise I'm not taking the product indicated by that phrase. Alright, now we're going to shift gears. We've been dealing with expressions so far. Now we're going to turn our attention to equations. In Chapter 2, we're going to talk about solving equations. For now, we're just going to talk about equations and their solutions, but we are not going to algebraically solve them. Look at number 54. The equation 2r plus 6 equals 8. And they want to know, is 1 a solution? The instructions say decide whether each equation has the given number as a solution. What is a solution? It is a value I can plug back in for the variable that makes the original statement true. So, very simply, we plug 1 in for r, and we see if it's true. I think you can do that one in your head. But for the sake of our notes and completeness, I'm going to go ahead and plug 1 in for r. You could use a dot there. I use parentheses this time. Standard notation when we're testing, we put a little question mark over the equal sign. This now reads, 2 times 1 plus 6, is that equal to 8? Order of operations, 2 times 1 is 2. And 2 plus 6 is 8. Yes, 8 equals 8. So, answer their question. Decide whether each equation has the given number as a solution. Because when I plugged it in, it made the original statement true. I can say yes, 1 is a solution to this equation. Number 56. Is 2 a solution to this given equation? Plug 2 in for x. Crank out the left-hand side and see if we get a true statement. Working in the parentheses first. 2 plus 3 is 5. Continuing to simplify here on the left-hand side, 6 times 2 is 12, plus 2 times 5 is 10. And finally, 22 equals 14. Nope, that's a false statement. When we plug 2 in for x, it did not make the original statement true. So is 2 a solution to this equation? No. What is the solution? Who cares? Right? Because that's not what we're being asked to do. We're just being asked to test. Is this a solution? Yes or no? Let's look at number 58. And we're asked to determine, is 12/5 a solution to this given equation? I'm sure many of you are certainly well familiar with the idea of combining like terms. Because we as a class have not talked about it, I'm going to pretend right now that it does not exist. You could use combining like terms and make the problem a little easier because cross-canceling will come into play. But I'm going to plug it in pretending I don't know anything about combining like terms. So, plug it in, crank out, and see if we have a true statement. 2 times 12/5 plus 3 times 12/5 plus 8, is that equal to 20? Little piece at a time. To multiply fractions, we multiply the tops, we multiply the bottoms. You recognize that this 2 can be written as 2 over 1. Now, get used to the idea that I'm not always going to write that. But here, I mean, it's early in the semester, I'll go ahead and write that over 1. Eventually, I'm not going to write that. So here in my first multiplication, as we follow the order of operations on the left-hand side of this equation, multiply the tops, multiply the bottoms. Plus, again, here we get 36/5. To add fractions, we need a common denominator. We already have one. So we add the tops, 24 plus 36, total 60. 60/5, that divides out evenly. 60 divided by 5 is 12. And then finally we can add here on the left-hand side to get 20 equals 20. That's true. So is 12/5 a solution to the given equation? Yes. Number 62. Here's another one I want you to try on your own first, and then we'll compare answers. Number 62, 7/10 x plus 1/2 equals 4. Is 5 a solution to this equation? So go ahead and pause the video now. You work that out and see what you get. We'll compare answers when you're done. To determine if 5 is a solution to the given equation, we'll plug 5 in for x. That gives me 7/10 times 5 plus 1/2. Is that equal to 4? We need to multiply fractions. You multiply the tops, multiply the bottoms. Cross cancel if possible. That 5 sits over 1. Whether we write it or just know it, doesn't matter. But the 5 is part of the numerator. We can cross cancel here. 5 goes into 5 once. 5 goes into 10 twice. I don't typically write the ones when I cross cancel because they don't do anything. If you want to write the ones, again, that's fine. We've cross canceled all we can. Let's multiply in the top. We have a 7. In the bottom, a 2. To add fractions, we add the tops. Write that result over the common denominator. So 7 of them plus 1 of them is 8 of them, 8 halves. 8 divided by 2 is 4. And this gives me a true statement. So was 5 a solution to this equation? Yes, it was. Let's do some more translating. Number 66. Notice the instructions. It says write each word statement as an equation. Use x as the variable. Then find the solution of the equation from the set 2, 4, 6, 8, or 10. So let's look at number 66. It says a number minus 3 equals 1. One thing I want you to pay attention to, you see that period? This is a whole sentence. The ones we were doing back up in number 40 through 52, they didn't have periods. They're phrases. So notice that phrases translate to simply expressions, while sentences will translate to, in this case, equations, or in some cases, inequalities, like that is less than. But this is a full sentence, and full sentences will typically translate into full equations, while an English phrase will translate into an algebraic expression. So let's translate. This one's very straightforward. A number minus 3 equals 1. No mystery there. And it says find the solution of the equation from the set 2, 4, 6, 8, or 10. That is, one of these should be a solution to that equation. Now, how are we going to find out? Because at this point, we are not algebraically solving equations, even if you know how to do that. What is she wanting us to do? She wants us to plug in and see if it works. I think we can do this one in our head. Plug 2 in for x. Does that give you a true statement? 2 minus 3 equals 1? No. Plug 4 in for x. 4 minus 3 equals 1? Yes. So my solution here is 4. we were asked to both translate and find that solution from this set. So we'll put a box around all of that. Let's try another one. Number 68. The product of a number and 3 is 6. The product of a number and 3 is 6. Now, strictly speaking, as we translate this, the product of a number and 6, this and is your multiplication sign, right? The product of a number and 6, I would write product of a number and 3, we would write x times 3. But in algebra, it is preferable to always have your numeric factor in front of your variable factor. So in this case, we will write 3x. I'd have to count it right if you put x times 3, no problem. But this is typical, having the numeric factor in front of the variable factor. The product of a number and 3, we've written that, is 6. Is your equal sign. And I think you can see what the solution will be. 2, 4, 6, 8, or 10, what works for x? When x is 2, 3 times 2 is 6. So my solution here is 2. Number 70. The sum of 6/5 of a number and 2 is 14. Let's talk about this 6/5 of. That's all I want to talk about at the moment. What does that indicate? If I were to ask you, let's come back to this in a minute. What is half of 10? What does that of mean? Don't say division. You're not dividing. Half of 10, you know half of 10 is 5. How do we get that using a half and a 10? Half of 10. You're multiplying. I understand why we think of division, because in my head, to take 1/2 times 10, I'm going to think 10 over 2. 10 divided by 2. But this of is a multiplication. When you have fraction of, or decimal of, or percent of, that of indicates multiplication. Half of 10, 1/2 times 10, the 10's over 1, cross cancel. Half of 10 is 5, of course. But when I see fraction of, decimal of, percent of, it is indicating multiplication. Let's return to our problem. The sum of 6/5 of a number and 2 is 14. Piece at a time. The sum of, well, that's addition. Where's my addition sign? Because it's got to be the sum of this and that. The sum of this and that. That and is the addition sign. The sum of what? Okay, so let me write. The sum of, I've already written in algebra, the sum of. The sum of what? This and that. Well, what's this? 6/5 of a number. 6/5 what? Times a number. 6/5 times a number. I'm going to tell you right now, this x had better be level with the fraction bar. Because if it looks like it's down here with the 5, I'm going to count that wrong. That x does not belong to the denominator. Okay, it's this fraction times that x. The sum of 6/5 of a number and what goes on the other side of my plus, that 2, is 14. Do you see how we've translated? The sum of what? The sum of 6/5 of a number and 2 is 14. Now, from the set, 2, 4, 6, 8, or 10. Find the solution by plugging in. Think as we do this one. What could you plug in for x that could possibly make this true? If 6/5 times our number we're plugging in plus 2 equals 14, a whole number, then 6/5 times x has to be a whole number, doesn't it? Which means that what I plug in for x is going to have to cross cancel with this 5 to get rid of the denominator. If I plug 2 in for x, will 2 cross cancel with the 5? Nope. So how could that possibly give me the whole number 14? It can't. I'm not even going to try the 2 or the 4 or the 6 or the 8. The only thing here divisible by 5 is that 10. So I'm not going to waste my time with the others. I'm going to check and see if 10 will work. This 10 is over 1. We cross cancel. 5 into 10 will go twice. 6 times 2 is 12. This is over 1, but we don't write over 1. So 6/5 of 10 is 12. Plus 2. Is that equal to 14? Yes, it is. So we translated, and we found that the solution from that set was 10. So there are the two parts of my answer. Let's do one more. Number 72. You might want to pause the video once we get this written up here. Try this one on your own, and then compare answers with me in a minute. $12 divided by a number equals 1/3 times that number. Now, let me take just a minute and indicate to you that 1/3 times a number could be written as 1/3 what? Of that number. That would be another way to write this. So if you saw 1/3 of that number, you would know that we're multiplying. Just like when you see times, you know we're multiplying. If you want to pause the video here and try this one on your own, go ahead and do that, and then we'll compare answers. All right, let's get to translating. You see where the equal sign is going to be. What's going to be on the left-hand side of this equation? 12 divided by a number. And how did I say I would like that to be written? 12 divided by a number x. Let's write that in the form of a fraction. That just makes life easier down the road as we do the algebra. 12 divided by a number equals 1/3 times that number. that x had better be level with the fraction bar, not look like it's in the bottom with the 3. So there's our equation. And now we're asked to pick a solution from that set, 2, 4, 6, 8, or 10. If I plug in 2 for x, does that work? That would give me what? 6 equals 2/3? Nope, the solution's not 2. What about 4? When x is 4, does that work? That would give me 3 equals 4/3. No, 4 is not the solution. Try the 6. That gives me 12 over 6 is 2. 1/3 of 6. However you want to do that, 1/3 of 6 is 2. You might set that 6 over 1 and cross cancel. But either way, that gives me a true statement telling me that the solution to this equation is 6. So that's our look at section 1.2, and you are ready to get started on that homework assignment.